Welcome to this presentation on the BFSS Matrix Model, also known as M-matrix theory. This groundbreaking framework offers a non-perturbative formulation of M-theory, proposed by Tom Banks, Willy Fischler, Stephen Shenker, and Leonard Susskind in 1996. Today, we will explore its origins, its connection to string theory, and its profound implications for our understanding of quantum gravity and the nature of space-time. Our objective today is then to explore the basics of the BFSS matrix model, known also as M-matrix theory, which is the oldest Yang-Mills matrix quantum mechanics proposed for quantum gravity or M-theory. In particular, we will try to understand the connection of this model to D0 branes, black holes, supermembranes, and non-commutative geometry. The original reference is the 1996 HEP preprint 9610043 by Banks, Fischler, Shenker, and Susskind. The BFSS matrix model was devised to provide a concrete definition of M-theory, an 11-dimensional theory unifying all consistent versions of superstring theory. It is closely related to other matrix models such as the IKKT model and the BMN model, each offering unique insights into the non-perturbative dynamics of string theory and M-theory. The BFSS model emerges from the dynamics of D0 branes in type 2A string theory. These D0 branes are point-like objects whose interactions can be described by matrix quantum mechanics. In the BFSS model, the D0 branes are represented by Hermitian n times n matrices, where n corresponds to the light cone quantized momentum and the number of D0 branes. At its core, the BFS model is a supersymmetric quantum mechanics of 9 n times n Hermitian matrices. It is formulated as a 0+1 dimensional gauge theory with 16 supercharges. This matrix model encapsulates the essence of D0 brane interactions and provides a framework for understanding their quantum mechanical behavior. Specifically, the Hamiltonian of the system, as discussed, incorporates the kinetic and potential energy terms of these matrices. The action of the BFSS matrix model, as given by equation 1, is fundamental to its formulation. It includes several critical components. R is the compactification radius, a crucial parameter in the model. Xi are n times n Hermitian bosonic matrices. There are 9 of them. Psi is a 16-component 9-dimensional spinor composed of n times n Hermitian fermionic matrices. dt represents the covariant derivative. A is the gauge field, facilitating the gauge symmetry of the model. Gamma I are 9-dimensional Dirac matrices that satisfy specific anti-commutation relations, as shown in equation 2. These elements together form the comprehensive action, which governs the dynamics of the BFSS matrix model. Path integral. The path integral formulation provides a framework for calculating quantum mechanical probabilities. For the BFSS matrix model, the partition function, as defined by equation 3, involves integrating over all possible field configurations of Xi and Psi, weighted by the exponential of I times the action. Gauge symmetry. The local gauge group of the BFSS matrix model is SUN, consisting of n times n unitary matrices with determinant 1. Physical quantities in the model are invariant under the gauge transformations described in equation 4. This invariance under SUN gauge transformations ensures the consistency and symmetry of the model. Supersymmetry. The BFSS matrix model is endowed with script n = 16 supersymmetry, which plays a crucial role in the stability and analysis of the model. Supersymmetry leads to cancellations of certain quantum corrections, aiding in the understanding of the spectrum and dynamics of the theory. The explicit supersymmetric transformations are given by equations 5, 6, and 7. These transformations ensure the invariance of the action under supersymmetry and provide a rich structure that protects against certain quantum corrections, thus ensuring the stability of the vacuum state. Let's explore the significant physical implications of the BFSS matrix model. First, M-theory and D0 branes dynamics. The BFSS model is fundamentally a proposal for the quantization of M-theory and the dynamics of D0 branes. It's conjectured to describe the discrete light cone quantization, DLCQ, of M-theory. This model captures the non-perturbative interactions between D0 branes, which correspond to light cone quantized momentum modes in M-theory. At low energies, the BFSS model simplifies to a quantum mechanics framework for these D0 branes, with their bound states representing various objects in string and M-theory. Second, black holes and gauge gravity duality. The BFSS model exemplifies the holographic principle, connecting to the gauge gravity duality, similar to the ADS-CFT correspondence. It provides insights into black hole physics by representing the microscopic states of black holes through holographic matrix degrees of freedom. In the large N limit, the BFSS matrix model can capture the gravitational dynamics of 11-dimensional M-theory, paralleling how the ADS-CFT correspondence relates higher dimensional gravity to lower dimensional boundary conformal field theory, CFT. Additionally, M-theory compactified on a circle can be described by the dynamics of D0 branes, akin to how ADS-CFT handles higher dimensional theories compactified to ADS spaces. Third, supermembranes and non-commutative geometry. In the BFSS model, the variables xi are interpreted as the Fourier modes of the transverse coordinates of supermembranes in the light cone gauge. This aligns with the holographic principle, where bulk gravitational degrees of freedom, such as membranes, are encoded in lower dimensional variables, such as matrices. The non-commutative geometry arising from the matrix model offers a natural setting for understanding holographic duality, where the matrices xi can be seen as coordinates in a non-commutative space. This leads to a deeper understanding of spacetime at the Planck scale. We can now summarize the non-perturbative dynamics of the BFSS model and their non-perturbative approaches. The BFSS model provides a non-perturbative framework for studying black hole physics in M-theory. Bound states of D0 branes can form black hole solutions, and their dynamics can be analyzed within this model, providing a microscopic understanding consistent with holographic principles. The model's non-perturbative dynamics also contribute to understanding the gauge gravity duality, with the dynamics mapping onto gravitational systems in certain limits. Determining the exact nature of the supersymmetric ground state and the spectrum of excitations is a non-perturbative problem, with supersymmetry playing a critical role in constraining possible states and ensuring stability. The non-commutative nature of the BFSS model leads to emergent geometry, where matrices xi are interpreted as non-commutative coordinates, and this geometry becomes commutative in the large N limit. Understanding the continuum and large N limits of the BFSS model is crucial for its connection to M-theory. These limits remain significant challenges, requiring advanced computational techniques and theoretical insights. Computational approaches, such as lattice regularizations and Monte Carlo simulations, are employed to study the non-perturbative regime of the BFSS matrix model. Lattice regularizations involve discretizing time and imposing periodic boundary conditions, allowing the study of the model's behavior in the strong coupling regime. Monte Carlo methods sample the path integral of the BFSS model, providing insights into the non-perturbative ground state, excitation spectrum, phase transitions, thermal properties, and the vacuum state structure. It is the DP branes that give rise to the matrix formulation in the BFSS model. A DP brane is a p-dimensional hypersurface on which open strings can end. This leads to gauge fields and other degrees of freedom on the brane. In 10-dimensional gravity, these DP branes are soliton-like solutions with finite tension and carry RR charges. The position of a D-brane is defined by fixing certain coordinates, meaning the brane extends in the x0 to xp directions and is localized in the remaining spatial dimensions. The coordinates x0 to xp parameterize the world volume of the D-brane. When open strings have their endpoints fixed on a D-brane, the D-brane acts as a boundary condition for the string. These conditions are Dirichlet boundary conditions for coordinates transverse to the D-brane and Neumann boundary conditions for coordinates along the D-brane. The endpoints of open strings can move along the D-brane, leading to a U1 gauge field on the D-brane's world volume. The tangential components of the vector potential represent internal gauge fields, while the transverse components appear as scalars from the field theory perspective, describing the D-brane's position and fluctuations in transverse directions. When there are n D-branes, the gauge group becomes U1 to the power of n, and the number of string degrees of freedom increases to n squared. Strings can connect different D-branes, leading to massive gauge fields with masses proportional to the distance between the D-branes. In the limit of n coincident D-branes, the gauge group becomes non-abelian UN, and all fields become massless. The action describing the dynamics of the gauge field on a dp brane includes the Dirac-Born-Infeld (dBi) action and the Chern-Simons term. The low-energy effective Lagrangian can be derived by reducing the 10-dimensional supersymmetric UN gauge theory to p+1 dimensional space. The action of the dp branes is given explicitly by equation 10. The scalar fields xi represent the positions of the dp brane in transverse directions. These coordinates are n times n Hermitian matrices, leading to non-commutative geometry. The potential energy of the matrices xi vanishes if the matrices commute. This is known as the flat directions, where the classical background solutions of the theory are given by diagonal matrices representing the positions of the D-branes. When the scalar fields xi acquire vacuum expectation values, the gauge symmetry is spontaneously broken to U1 to the power of n. Let's explore how D0 branes lead to the emergence of gravitons in the context of the BFSS matrix model. We start with compactification. Compactification is the process of reducing the number of dimensions in a theory by curling up one or more dimensions into a compact space. In M-theory, compactifying one spatial dimension on a circle of radius r results in type 2a string theory. Both 10D type 2a string theory and 11D M theory preserve significant amounts of supersymmetry. In 11D, M theory has 32 supercharges. Upon compactification, these reduce to match the 16 supercharges of the 10D theory. The fundamental length scales involved are the 11D Planck length and the 10D string length. The relationship between these scales and the string coupling constant links the radius of the compactified dimension and the string tension. This is given by equation 12. M theory can be viewed as the strong coupling limit of type 2a string theory. Massless states in M theory correspond to an 11D graviton and its superpartners. Upon compactification, Kaluza-Klein modes arise in 10D, with zero modes corresponding to the massless fields present in type 2a supergravity. The momentum modes correspond to D0 branes in type 2a string theory. In other words, these D0 branes are interpreted as massive Kaluza-Klein modes, which are states with quantized momentum along the compactified dimension. Thus, D0 branes in 10D correspond to 11D graviton. The action for D0 branes in type 2a string theory derives from the reduction of the 11D supergravity action. The low-energy effective Lagrangian of the theory can be obtained by reducing the 10-dimensional supersymmetric UN gauge theory to a one-dimensional space. This action includes terms representing the dynamics of scalar fields corresponding to transverse coordinates and fermionic fields. This action is given by equation 13. In summary, D0 branes in the BFSS matrix model provide a way to understand how gravitons arise in M theory through compactification and the dynamics of Kaluza-Klein modes. This framework bridges the gap between higher dimensional theories and lower dimensional string theory descriptions. Let's discuss the discrete light cone quantization (DLCQ) and its role in obtaining the BFSS matrix model. In DLCQ, the light cone coordinate x superscript minus is compactified on a circle of radius r. This leads to the quantization of the light cone momentum p superscript plus, introducing discrete momentum modes that simplify the analysis by breaking down the theory into simpler components. The infinite momentum frame, IMF, is a reference frame where the momentum along a chosen direction, typically x superscript minus, is taken to be infinitely large. This simplifies dynamics by focusing on transverse components, treating longitudinal dynamics as simpler perturbations. IMF can be seen as a special case of DLCQ. Both approaches result in similar Hamiltonians for the BFSS matrix model, concentrating on the transverse dynamics of matrices Xi. The difference lies in the treatment of longitudinal momentum, continuous and large in IMF, discrete in DLCQ. Let's describe the formulation of the DLCQ in some detail. In M-theory, 11 coordinates xm are split into 9 transverse coordinates xi and 2 light cone coordinates x superscript plus and x superscript minus. The momenta p subscript plus and p subscript minus are conjugate to these coordinates. The metric in this frame simplifies the energy expression for massless modes, leading to a non-relativistic formula for energy. The longitudinal coordinate x superscript minus is compactified, making it periodic. This compactification quantizes the longitudinal momentum p subscript minus as in equation 21. DLCQ preserves a significant portion of the original theory's supersymmetry. In the light cone gauge, it maintains 16 out of the 32 supercharges. It also simplifies the dynamics by focusing on transverse modes and discrete momenta, crucial for the BFSS matrix model's formulation. The DLCQ provides therefore a natural setting for the holographic principle, encoding higher dimensional dynamics into a lower dimensional matrix model, essential for the non-perturbative formulation of M-theory in the BFSS model. Let us now outline more explicitly the DLCQ quantization of M-theory. First, recall that M-theory is an 11-dimensional theory unifying all consistent superstring theories and supergravity. In the low energy limit, it reduces to 11-dimensional supergravity. Type 2a string theory is, on the other hand, a 10-dimensional theory with both open and closed strings, including D-branes that carry RR charges on their world volume. Second, and as we have already seen, the graviton in the 11D M theory corresponds to D0 branes in type 2a string theory when compactified. The momentum modes in the compact dimension correspond to these D0 branes, linking 10D and 11D dynamics. More precisely, D0 branes in 10D correspond to 11D gravitons with longitudinal momentum equals 1 over r. The bound state of n D0 branes corresponds to a graviton with longitudinal momentum equals n over r. A careful analysis shows that the BFSS matrix model relies really on two hypotheses. First, the fundamental degrees of freedom in M-theory, when formulated in the light cone gauge, are nothing less and nothing more than the D0 branes. The second hypothesis states that the low-energy effective action of D0 branes describes the complete quantum theory of M-theory. This action is given by equation 22. By reducing the Dirac algebra from 32 dimensions to 16 dimensions by using the Majorana-Weyl condition, we obtain the Lagrangian in equation 23. The equations of motion are shown in equation 24. Both quantized supermembranes and non-commutative emergent geometry originate in the matrix theory from these equations of motion. The corresponding Hamiltonian of the BFSS matrix model is derived in equation 25. It is positive definite and has a complex ground state due to the interplay between discrete and continuous spectra, as well as the presence of flat directions. In this last section, we'll explore the relationship between supermembranes and non-commutative geometry within the BFSS matrix model, also known as M-atrix theory. M-atrix theory, in the large n limit, relates to the dynamics of supermembranes, which are higher dimensional generalizations of strings. The BFSS matrix model can be viewed as describing a quantized supermembrane inherently linked to non-commutative space. We illustrate this with membranes of toroidal topology, corresponding to a non-commutative torus. We introduce two unitary matrices, G lapse operator and H shift operator, in the general linear group GLN. These matrices satisfy specific commutation relations, which, as n tends to infinity, correspond to coordinate and momentum operators Q and P on the non-commutative torus. These are given in equation 29. Indeed, as n approaches infinity, the matrices G and H become operators in an infinite-dimensional Hilbert space. The non-commutativity parameter theta, which is equal to 2 times pi divided by n, vanishes in this limit, leading to a commutative or classical space, where Q and P become ordinary numbers. The while map between operators in the matrix model and functions on the non-commutative torus is given in equation 31. Correspondingly, the matrix product between operators is replaced by the Moyle-Weil star product between functions, and the trace in the finite-dimensional Hilbert space of matrices becomes an integral over the phase space of the torus. We obtain thus the structure of the non-commutative torus, which admits also the interpretation of the quantized supermembrane, as is evident from the Lagrangian derived in equation 34, which is nothing else but the supermembrane Lagrangian in the light cone gauge. As we conclude this presentation, let's reflect on the significance of the BFSS matrix model in the realm of theoretical physics. The BFSS matrix model stands as a cornerstone in the quest for a non-perturbative formulation of M-theory. Its framework provides a concrete and comprehensive approach to understanding the complex dynamics of D-branes and their interactions, bridging the gap between various dimensions and theories. The model offers profound insights into the nature of spacetime, quantum gravity, and string theory. By translating the intricate dynamics of higher dimensional theories into a matrix formulation, it allows us to explore the fundamental aspects of our universe in a non-perturbative manner. The rich mathematical structure and deep physical implications of the BFSS matrix model continue to inspire ongoing research in theoretical physics. Its contributions extend beyond immediate applications, driving advancements and opening new avenues for exploration in quantum field theory, string theory, and beyond. In summary, the BFSS matrix model not only provides a powerful tool for probing the mysteries of M-theory, but also enhances our understanding of the fundamental principles governing the universe. As research progresses, we anticipate further breakthroughs that will continue to shape the future of theoretical physics. Thank you for joining us in this exploration of the BFSS matrix model and its far-reaching implications. Stay tuned for more insights and discoveries in the fascinating world of theoretical physics.